All right, hello everybody. I'm Austin FitzGerald. I've been working with Dr. Slent and some of my wonderful teammates here. This summer I've had the opportunity to have a couple 100 million lines of data overall on student grade data from 2013 to 2018 of all people who graduated or were dismissed from computer science and software engineering. We wanted to use this to figure out why students struggle in our program and overall, and if we can prevent them and predict if new students are going to struggle. So without proper tools, academic advisors and students are left guessing whether or not they're going to succeed. A lot of our issues right now are due to a lack of analytical tools, no quantitative analysis of whether or not a student is actually going to succeed in the future. So students are left wondering. I'm sure you've dealt with this, all the students in this room. You show up to your advising meeting to choose classes, and you sit there, and neither you nor your advisor know why you're choosing those classes. You have to choose certain classes, and you don't know why. You don't know if you're going to graduate. You don't know when you're going to graduate. And it seems like everybody else is kind of in the same boat, so that's okay. But I'd like to kind of pick that boat up and move it somewhere else if possible. So this is our data set. Our base raw data set, we have 689 unique students. These are just students who graduated or were completely dismissed between 2013 and 2018. So our grade data is going to go back until 2007 about for students that graduated in 2013 and were there a little bit longer than normal. We have 820 unique courses, so our course selection is not completely limited to CSSE courses only. We also have random other courses that were offered one semester ever, and one person ever took them, and it made our data set very hard to work with. So this is what our raw grade data looked like. We had about 23,000 rows of this, and we could extrapolate many different features from that. So what is academic struggle? I keep saying that word, struggling, but if we really want to find a definition for it, then we can. We worked with Dr. Slent, who is an academic advisor, as well as got input from other faculty and from our data about what struggling is. And we decided to split up into two different parts. We have regular struggling, which is fairly common. It's either you get less than a C- in a course in a semester, which is usually a failing grade in most core courses, or you end a semester with a GPA less than 2.0 for that term. We have another definition which is severe struggling, and that is receiving an F in 2 or more courses in a single semester. Usually students who receive an F in 2 or more courses in a single semester are then put on probation. So it's good to create 2 different groups here. Because as we can see from our data, a lot of people struggle, a lot. This is CSSE, and this is both people who graduated and dismissed from 2013, 2018. And I don't think it's fair that a lot of people struggle, to be honest, because this is a lot of people, and if we're going to create our definitions like this, which everybody I've talked to seems to think they're pretty fair definitions. This is a lot of people. But we can see that people struggle less over time. And if you want to call that continuous improvement, I'd slightly agree with you. The longer you're here, the better you're going to do. But also, the longer you're here, the less likely you are that you already dropped out. As we can see here, you got terms taken on the x-axis and number of students on the y, and we can see how many people have actually struggled. This is actually only people that were completely dismissed from the university. So we can see that the number is going to get really small because people keep dropping out. Our did not struggle ratio is pretty small all the way throughout. But we want to prevent this. This is why we have the 2 different definitions here. We can see in a first semester, students severely struggling is pretty high, and then they don't come back. This happens a lot. We can't predict how a student's going to do with our data set, maybe in the future, off of how they did in high school. So there's no quantitative analysis here. But how they do in their first semester is really indicative of how they're going to continue to do. If you struggle your first semester, you're probably going to struggle your next. So, using that, hopefully we can figure out some ways to make people struggle less in their next semesters. These are overall students, so you can see that, again, the longer you stay, the less like you are that you already dropped out. But we can see over time, students do tend to do better. We want to keep them here longer. If you struggle early on, that's fine. Struggling is normal. But we need to keep you here. Again, we can see that people do better over time. This is the average term GPA per number of terms taken for all of our students. So the longer you stay here, the better you're going to do over time. And yes, we had a lot of people stay longer than 8 terms here. Staying longer than 4 years, about 43% of people who graduated stayed longer than 4 years. Which I personally would like to get that number down. There's only so much you can do. So our big picture. We know that students struggle, right? We know it's pretty common. We know there's 2 types. There's the type that's going to get you kicked out of school, and there's the type that's going to make you graduate with a low GPA in 6 years. We don't really like either of them, but it's good to signify between the both and hope that we can predict for both of them. So how far in the future, with varying amounts of past data, so whether you've been here for a year or if this is your 5th year here, how far in the future can we predict if you're going to struggle? So we have our experiments here. Number 1, let's predict a student's next term GPA using their previous term GPA. If your previous and next term GPAs are pretty correlated, then we should be able to predict them with low error and medium accuracy. Given varying amounts of past performance data, can we predict if you're going to graduate? So given your term GPAs through 1 through n semesters, so your first 3 semesters, your first 5, or if you've only been here 1, can we predict if you're going to graduate? And number 3, we want to see how you're going to do in future courses exactly. So given your prerequisite data, how you did in the courses that you had to take, how are you going to perform in this next course? So this is our first experiment. Next term GPA prediction. So how we set it up, I'm going to have to read off this, I'm sorry. How we set it up was for all spring, fall semesters, we find a non-null GPA for each student. So imagine we have this long data set of all of their semesters and their GPAs. We take only the semesters where they actually took any courses. We shrink that down for every single student. And then we're going to push all of them to the left. Okay, so we no longer go by term number, we go by number of terms taken. So your second term taken, what GPA did you have? Your third, your fourth, etc. We do this for every single student. We're then going to choose a random term pairing. So consecutive terms, your third, fourth, your fifth, sixth, seventh, eighth, etc. And we are going to create a data set based off of that where we want to choose some term pairs that are indicative of our actual data set of our distribution. So we can see here we've got a graph on the bottom left of the term pairs that we chose from our data set. Each one is within 1% of its expected deviation from the actual complete data set. And we did have some people here who took 13 and 14 terms. We then generated a 5-fold stratified training and testing sets based off of this data. We did this based off of the term number, which if you know something about stratification, it's usually not done off that. It's usually done off of your feature. But it's hard to stratify based off of continuous data. So here's how we did it. We had a few models that we ran with. So with our term pairings, we ran with gradient boosted trees, linear regression, neural network, and our 0R, which was most frequent. That was actually a mean, I'm sorry, which was our baseline. So it was kind of, in a sense, flipping a coin, but not really. So how I said it was cross-validated. So with a bunch of our pairings, we could train it in a few different ways. Each one of our models spit out different error metrics, so we could determine how well they performed overall. We then used a 95% confidence interval to compare the models to each other. As you can see on the bottom left, this is the performance in our normalized error. Our root mean squared error was originally came from on a 4-point scale, because that's what GPA is based on. So it's normalized in the sense it's just divided by 4. So as you can see, our error is pretty low for all of the models except the baseline. And then they all perform pretty similarly is the issue here. We don't have a model, even after tuning them, that performs much better than anything else. But our error is pretty low, so we can predict your next term GPA fairly well, fairly accurately based off of your current term GPA. Next, we want to predict if you're going to graduate. So based off of your term GPAs for your first, second, third, fourth, fifth semesters, can we predict if you're going to graduate? So for each student, we're just going to take all of their term GPAs like we did, and we're going to push them all to the left, like I said. So we're going to say, okay, you've been here this many semesters, not you were here fall of 2016. We're going to generate a 5-fold stratified testing and training sets, again, this time based off of their graduation result, which is binary. So either 0 or 1. They graduated, or they did not graduate, or they did. So we want to make sure that our results are indicative of what's actually happening. Each model spit out AUC and accuracy. So AUC is so we can kind of compare the performance of the models against each other. And the accuracy is to determine whether or not they predicted the graduation result correctly, exactly. So we ran our models based off of our data. And we can see the performance of them here. What we did was we bootstrapped them and ran a 95% confidence interval. So we can see that our models perform better than the baseline. And we have a clear winner with logistic regression. We can predict whether or not you're going to graduate about 86% accurately. So with your previous data, it varies. So it's harder to predict if you're going to graduate with 1 semester of data, and it becomes easier with 5 semesters. But we can do it. And our next experiment was one that took quite a while here, and it's a pretty good one. So we want to predict in a post-requisite, we want to predict that grade based off of how you did in the classes that you had to take to get there. So what we did is we manually mapped out, and thanks to Henry and some other guys here, this took a while because our school doesn't exactly have a data set for this. The course structure for computer science software engineering. So this is all the core courses as well as some electives that you need to take other courses. We then digitized this. We made some cool graphs out of it, and we created a recursive grammar structure. So pretty much using a lot of logical expressions. So in order to take, let's see if I have that up here. In order to take database design and implementation, there's your logical expression that you have to have taken the other courses. We can use this to make a tree. So with each node being a different course, and we can have their edges be the grade required to go between them, we can create a completely direct acyclic graph based just off of our course structure. Using that, there's a couple different things we can do. We can iterate over it, and we can grab data, and we can run some models to determine how you're gonna do in a post-requisite based off of given prerequisites. You can directly plug it into a Bayesian network if you'd like, which we are working on at the moment. So what we did is the first one first. So we wanted to kind of go through and see, okay, which prerequisites are the best for determining what you're going to get in the post-requisite? Is it the immediate ones? So that's what you see up top here. In order to take discrete, you had to have taken Calc 1. That's the immediate ones. So what you have to take to get to something directly. Or there's root. So the bottom of the bottom. So for calculus, the bottom would be basic algebra. Given students who took basic algebra, what did they get in calc? And we can use that to train our model to determine how future students will do in that course pair. We have all. So with all prerequisites, everything for a given post-requisite. All of the grades we can get, how can we predict if they're going to do? Or how can we predict how they're going to do? It's okay to have missing data. I just want to mention that. So a student doesn't have to take all the prereqs. There's a lot of or relationships, right? So you can take this class or this class. And that makes advising a little harder, but you can do it. So it's okay to have missing data. Our model's fine with that. So here are our results. Let's skip right into it. We had our trees, and we created some big data sets based off of it, iterated through them, and grabbed all of the student grade data for each course, threw it all in, and said, here you go, model, just take care of it. So our results are pretty good. After some trial and error, actually using some features that we thought would work, but apparently giving a predictive model too much data, it doesn't work sometimes. We got some pretty good results. We had to print 4 or 5 posters for WSTS because the first 4 did not work. But our accuracy is actually scarily high. So there's been I think there's been more analysis into why these results are so good than there is into like how we got them. But we can see that for predicting a post-requisite using all prerequisite courses, so all of the data we can possibly get for any course related to that course in the course structure, we can predict using gradient boosted trees classifier exactly on an A to F scale, A minus, B minus, et cetera, exactly what you're going to get in that course 86% of the time. Now, we need to do some further analysis and bootstrap in and run some confidence intervals to determine just how likely it is that these results are completely true. But based off of our data set, this is exactly what we've gotten. And we can predict within a full letter grade, so A to B, C to B, what you're going to get in a course with 99% accuracy. Our normalized root mean squared error is also pretty darn low, a lot lower than our baseline, so 0.09 compared to 0.28. As you can probably see here, our logistic regression underperformed for everything except for the immediate prerequisite courses. You might be surprised to learn that we can predict using your root prerequisites, so how you did in those classes you took long ago, we can use those to predict how you're going to do better than we can use the ones you just took. Again, some further analysis needs to be done here, but I've gone over this and checked it a few times, and as you can see here, with gradient boosted trees, using that course you took long ago, we can predict with 82% compared to 33%. So that's a pretty big difference. So overall, our models perform well. We can predict how you're going to do in a post-requisite course using your prerequisite data easily and well. This is where I would have done a demonstration, but like Ross, can't do that, so that's okay. I went through and took some screenshots of the application we made for advisors. So using these models, we saved the models for each and every course. Oh, and I forgot to mention, we went through and tuned all these models too. So we have a different model for every single course setup. Every single all root and prereq, or all root and immediate, as well as every single course, we have a different model. So everything's unique. You can plug your data in and expect that it's only going to be working with that. So what we have here is an application for advisors. It's a work in progress, but everything that I'm showing you works on it. So on the left, you have all the post-requisite courses that you can choose. You have above it, you can choose whether you'd like to enter grades for its immediate prerequisites, for its root prerequisites, or for all prerequisites. On the right-hand side, in that blank box in the middle, well, mostly blank, you can see that Introduction to Software Engineering has 3 prerequisites in the course Computer Science Software Engineering structure. You can enter the grades for it from an A to F scale for what a student has gotten in them so far. in this case, they're about to take Introduction to Software Engineering. So you can enter their prerequisite grades. You can enter for the earliest prerequisite, their term and cumulative GPAs. And you can enter whether or not they've struggled. So those are the 3 definitions we talked about earlier. You can use the 2 different models we have here, logistic regression and gradient boosted trees, and click Predict. And boom, here's the probabilities for each of the grades that they're going to get. These are not just probabilities for, okay, these people performed similarly, so we're going to pull out how they did. But we can see here that using our data, this is how we're going to predict they're going to do. So we've got. I expected the demonstration to take longer, but I'm actually happy now because I get to present some other stuff we found. Not exactly our experiments, but some cool stats that I did on the side or we did to figure other things out. So here's some course grade correlations. I'm pretty proud of this one. So we took every single course in our data set. I don't remember exactly how many courses I said that was, but it's a lot. We then found all possible combinations between those 2 courses and singled out the ones where we didn't have any students take either of those courses together. So we grabbed all of the grades for each course combination. So Calc 2 and 20th century history. I don't know if that's a real class, I'm sorry. All of the grades between those, and we want to see, okay, are these grades correlated? Is what you do in this class indicative of how you're going to do in the other class? This is useful for the prerequisite structure as well as just random courses. So I ran some machine learning algorithms through Machine Learning Studio in Microsoft Azure, and this took quite a while. I imagine going through all this. You can imagine going through all this data. We ran Spearman's ranked correlation coefficient process on each course combination. So with all the letter grades, can we see if there's a monotonic relationship between those 2 course grades? So I want you to imagine a scatter plot here. On the y-axis, you've got Calc 2, and it's all of the grades that a student received in Calc 2. On the x-axis is Calc 1, and it's all of the students' grades they received in Calc 1, where the dot shows what they got in both. If we can see a monotonic relationship there, that's good. We can show that these 2 courses are correlated. So our results here, it's actually pretty surprising. Firstly, introductory courses that people may consider easy A's, have similar grade distributions, and therefore they're correlated. This does not mean that how you do in I don't know, let's say introduction to UW, is that what we call it, intro to UWP life? I forget. It's not saying that's the exact same you're going to do in, let's say, introduction to psychology, but I think it's because that one's not an easy A. But if with introductory courses, they have similar grade distributions. So we can see that, they're fairly correlated. Courses within the same department. So your math courses are going to be similarly correlated to math courses. But what we did not find was that immediate prerequisites were very correlated. Most classes that have high correlation scores, so high row values, are not actually immediate prerequisites. So maybe that has something to do with why we can't predict immediate prerequisites very well. In order to validate this, we wanted to validate for type 1 error, so to get rid of the chance that this is just random. We used Bonferroni's correction, and what this did was adjusted our p-value to be a lot lower so we could take out everything that we didn't find statistically significant. Here's our course structure for the CSSE with the adjusted row values. So you can see that we have 2 course pairings here where there's actually a pretty high correlation, above 0.6. Everything else is not very correlated. This is interesting, and we want to delve deeper into it. Another interesting find we had is there's no negative correlation. So we couldn't find any statistically significant course combinations where you were going to do worse in one course if you did better in the other. That was actually disappointing for me because I just like finding outliers, but that's probably a good thing. Here's something else we did. So we've had some fun with this one, and I just wanted to show it real quick. Over time, we have noticed, at least in CSSE, that people get a lot more A's than they should. People fail a lot less than they used to. So you can see on this graph right here, the dark green being the A grades, light green being B grades, whatever that color is in the middle being C grades, etc. That's a trend line. People have been doing a lot better, a lot more recently, and have not been failing as much as they used to. Continuous improvement. Maybe they are just doing better, or grade inflation. Maybe they're earning grades they don't deserve. We can also see this here, where we can see that term GPAs are on a slow rise over time. So you can make up your mind on that one later. Our future work. So in progress, I mentioned that we are working on a Bayesian network at the moment. Nate Brockhoff, who is not here right now, he has put a lot of hours into it. Sadly, we couldn't get it finished before all of our grants ran up, but I hope to hopefully continue it during the school year, because that actually will hopefully perform better than our, let's say, gradient boosted trees did for the post-requisite prediction. And it will be a lot more useful in the future. Later on, it'd be nice to expand into more departments. There's a lot of data out there, through the couple million rows that we ran through. I would personally like to do the same thing for other departments. Call me crazy, I love Excel, but seeing that much data, really, I love it. More generalized web-based application. So our application we threw together, it was kind of last minute. We had plans early on to develop a web application for advisors to use all of the different models and feed as much data as possible into it to determine if a student will struggle and if it will be severe struggling. We didn't get around to it, but the data is all there, and a lot of the code is there. So hopefully in the future, either I or someone else can get to do it. And like I mentioned with course correlations, it'd be nice to do a deeper dive into determine the effectiveness of our course structure. So the prerequisite structure, how you're doing right now in this course compared to the course you have to take next, is if those are correlated, how important is it? And if they're not, how important is that? So it'd be nice to study further into that. There's a lot more to do with this, and I think at least our findings here show that there's some interesting stuff to look into. We do have a working application for advisors or students to use to determine the likelihood of how they're going to do in a future course. And this is now a quantitative means, and even though I'm sure there are advisors out there who have been here for 40 years and can look at a student without even knowing their name and say if they're going to pass or not, it's nice to have some quantitative analysis here. So conclusions. Like I said, you can predict it. You can predict if students are going to struggle. We could predict their next term GPA fairly well. We could predict if they're going to graduate even better. And we can predict their post-requisite course grades. With more data comes more responsibility, but it'd be nice to make these models work even better. So with these findings, we hope that academic advisors will in the future be able to use something like this. There's not a lot of tools out there for everyone to use, and it'd be nice if there were. You can check out all the code, and there's graphs and more statistics and all my random ramblings on our GitHub. So feel free to do that if you're interested at all. If not, I don't blame you. So thank you. I want to say thank you to everyone. I mean, this SUSP thing has been a blast, so thanks.